being here. Our concert tonight features pieces that are inspired by science. So we have spiders and bees and night. You'll hear lots of interesting text tonight. We are thrilled to have scientists from the Science, Policy, Education, and Communication Club at UT Southwestern join us as our interlude artists tonight. They will be answering some of our singers' science questions, and they will also be performing live science experiments right here on the Meyerson stage, possibly a first. Please join me in welcoming them to the stage.
SPEaC. We're a group of graduate students and postdoctoral fellows from UT Southwestern Medical Center here in Dallas. And the goal of our organization is to raise awareness for science policy and how it affects research and medical care. We also provide opportunities for our members to learn how to more effectively communicate science to general audiences and to also promote science education through doing outreach efforts here in the DFW area. So tonight we'll be performing experiments during the interludes to help add to the entertainment through the power of science. And we're also going to be answering questions as well through an extension of our Ask a Scientist program. And this is a program where we obtain questions about just general science questions from the community, and we answer these through a video response, and we post these on our YouTube channel. So we have some questions from some of the choir members here that we're going to answer tonight. And so with that, we'll let Jonathan take it away with the first question.
Thanks, Sharon. So this question comes from Reagan. She's a member of the Prelude Chorus, and she asked, why is the sun hot? Well, Reagan, the reason is that the sun is made up of a lot of hydrogen, which is a component of a lot of things that you might know about, like sugars or water involves a lot of hydrogen. And what happens is the gravity at the center of the sun pulls those hydrogen atoms together really, really closely to the point that they actually undergo something called nuclear fusion, which sounds really sciencey and really scary, but actually it's just the force of gravity causing those hydrogen atoms to join, and that releases a lot of heat. And so there's countless hydrogen atoms in the sun, all combining to release heat. And we can feel just the right amount of the warmth from that sun here on Earth over 93 million miles away. That is a lot of heat. So that's your answer, Reagan.
Thank you.
That was great. But did you guys know that you can use carbon dioxide to make music? Does anybody know that? Because you can. You can absolutely use carbon dioxide to make music. You know, carbon dioxide is in the air all around us, and if you were to take those individual carbon dioxide molecules and get them really, really cold and really close together, they condense to form solid carbon dioxide, which we commonly refer to as dry ice. So dry ice, unlike water, which water, when it's frozen, you add a little bit of heat and it becomes liquid water, and then you add a little bit more heat and it becomes water vapor. Well, carbon dioxide at the temperature and pressure in a room like this goes immediately from solid to a vapor, which you can kind of see it doing right there, and that's a process called sublimation. We can speed that up if we add some of this carbon dioxide to liquid water, which creates this cool little fog that you can see here and also in our demonstrations out in the lobby. Looks pretty fun. Basically, it's simply carbon dioxide going from a solid to a gas really quickly. But if we do the same thing, instead of in a large beaker like this, but in these small bottles or in this kettle, you can hold on to that, we can harness that release of carbon dioxide gas. And we're going to try an experiment here to see if we can do that and at the same time make some music with this whistle and this kettle and these horns. So let's go ahead and give this a try. We have here science in action, and it also looks really cool. We got a lot of pressure. Come on, sound horn. Woohoo! Excellent, thank you guys. Thank you very much.
Okay, our next Ask a Scientist question comes from Penelope of West Dallas Community School, Class 4. So Penelope asked, what is snail slime made of? Great question. Snail slime is actually just mucus. So we're all familiar with mucus, but you probably don't think about it much unless you're sick, you have a cold, and you're producing more mucus than you would normally produce. Snails actually need to produce mucus all the time in order to survive. So most of their body is protected inside of their shell, but there are parts that are exposed to the outside that need to be kept wet and kept from drying out. So the mucus helps them keep those parts from drying out. But it also acts as a lubricant and helps them move along smoothly and efficiently. So if we think of our own mucus, snail slime is actually also sticky. And it's sticky because there's special proteins inside that help them move along the ground, the flat surface, but also helps them move up vertical surfaces as well.
This next question comes from Cassie, a member of the Concert 2 chorus. And she wants to know, why do I feel worse when my body is fighting an illness? When we get infected with a microbe, usually a bacteria or a virus, our body has to fight back to keep us healthy. Fighting is damaging, but it also takes a lot of energy. Sometimes the microbe has weapons that make us feel bad, but we have special immune cells that can recognize the attack, try to keep the pathogen at bay, and send for help. This help comes from stronger cells that actively kill the pathogen. But as I said, this all takes a lot of energy, which is why we feel more tired when we're sick. The immune system also alters the body to make it so that it's harder for the microbe to survive. During many viral infections, the body's temperature increases, which we call a fever. This makes us feel really bad, but it also helps to clear the infection. In fact, many of the general symptoms of sickness, including fatigue, runny nose, joint pain, and fever, can all be attributed to the body's efforts to get rid of the pathogen.
Organisms communicate in many different ways, such as verbally using sounds or words, by touch, movement, or other methods. Have you ever heard bacteria talk? Well, tonight we brought with us a special type of bacteria, and they communicate using chemicals. They make these chemicals themselves, and when there are a lot of bacteria all together, they each start to recognize these chemicals. And once there are a lot of chemicals they're being made, a lot of bacteria, they start producing light, a process called bioluminescence. So bioluminescence is not specific to just the bacteria. Other organisms such as jellyfish and fungi can also bioluminesce. But these bacteria don't have eyes. They can't see the light. Why would they make it? Well, it's an evolutionary advantage for them to survive. These bacteria live inside a particular type of squid in the ocean and act as a shield for the squid. So when the squid is looking for food at night, it's up near the surface of the ocean, and the moonlight coming down would normally project a shadow of the squid, so predators below could possibly see the squid and eat it. However, because the squid has these bacteria in it, the bacteria produce light, so the shadow is prevented from being made. So the squid is then protected from the predators and can go along happily eating. So this bacterial-squid interaction is what we call a symbiotic relationship. This means that they both benefit each other. The bacteria get a nice home, and the squid is protected from predators, and we get to see the beauty of this biology. So here we have 3 different cultures of the bacteria, and now we'll observe this in the dark. So please dim the lights and observe the bacterial bioluminescence. All right, you can turn the lights back on, please. Thank you.
All right, our next Ask the Scientist question comes from Morgan. Morgan's from West Dallas Community School, Class 5. And Morgan asks, why do we put chemicals in our food? Well, there are two good reasons for us to put chemicals in our food. The first one is, well, to keep our food from going rotten. See, we don't always get to our food right away like the food we get in grocery stores. So we put in things like antioxidants to keep our food from spoiling. The second reason why we put chemicals in our food is in order to help us get all the nutrients that we need from our diet. So some foods like milk and orange juice are fortified or have added calcium and vitamin D to help keep our immune systems healthy and help keep our bones strong. That's why we put chemicals in our food.
This next question comes from Lena, and she's a part of Concert 1 Chorus. She wants to know what causes the hair to turn white. A lot of parents would say that the stress due to children is the cause of their graying hair. But science has proven that stress does not cause hair to go white. In fact, when everyone ages, their hair starts turning white. Hair is made up of a protein called keratin, which is actually just white. And you have different cells in the scalp that produces pigment. These pigments mix together and coat your hair that gives all of us different hair colors. With time, these cells start dying or they become really bad at producing the pigments. So your hair starts graying. And a lot of factors could contribute to hair graying, and some of them are hormones, imbalanced diet, exposure to toxins. While children don't give their parents white hair, parents definitely determine when their children will get gray hair. Genes which we inherit from parents, they're the most important factors that determine when you'll start getting gray hair. So if you start getting gray hair soon in your life, you can blame it on your parents.
Wow, I am really impressed with what I've heard tonight. These are some really great singers. I also like to thank the audience for being here, because it's great to have a lot of support for these singers, and in particular the teachers who have helped these students rise to such a great level of singing. The teachers are in a way a catalyst for this process of becoming these great musicians you're seeing before you. And we have an example of a chemical catalyst for you here. In these little cylinders behind, we have sodium iodide. This is a mineral we eat every day in our salt. It's good for us. It helps our thyroid stay healthy. And in the big cylinders, we have, for fun, some soap. We have some food coloring. And we have some hydrogen peroxide. It's something you might use to clean a little scrape on your knee or something like that. So what's happening right now, and you can't really see, and most of these bubbles are actually from the soap, the hydrogen peroxide is breaking down. This is a really slow process. But when we add the catalyst, you'll see. Can you see it here? It's coming out of the tube. Yeah. So this is why we call it elephant toothpaste. You see the green, and you need a lot of it for those tusks, right? So that was fun. Let's see if we can get it to go a little bit faster with a little more of the catalyst. Yes. All right, so that's elephant toothpaste. And I'd just like to mention again, catalysts are great. They help students rise to new levels, and they help chemical reactions happen all the time. And so I'd also like to thank my colleagues who have been backstage and on stage that you've seen here. Thank you so much.